Problem 6.150 or 7.133 for the given textbooks. For details, please see the description below. Cold water at 10 Celsius enters a water heater at a rate of 0.02 meter cubed per minute and leaves the water heater at 50 Celsius. The water heater receives heat from a heat pump that receives heat from a heat source at 0 Celsius. Assuming the water to be an incompressible liquid that does not change phase during the heat addition, determine the rate of heat supplied to the water in kilojoules per second. And assuming that the water heater acts as a heat sink, having an average temperature of 30 Celsius, we need to determine the minimum power supplied to the heat pump in kilowatts. For the calculations, we need to find the value for CP in a specific volume. We go to the back of the book, table A3, and we find that for CP we have 4.18 kilojoules kilogram Kelvin, and the value for the specific volume is equal to 0.001 meter cube per kilogram. Notice that the assumption is we're treating water as an incompressible liquid. Now what we need to find is the amount of heat rate supplied to the water that is equal to the value of Q dot H, and that is simply going to be the mass flow rate times the value for CP and the difference between the temperatures that we're going to have. So what we need to calculate is the mass flow rate. So the mass flow rate is simply going to be the volume flow rate that we have divided by the specific volume. In this case, we have 0.02 meter cubed per minute, and we do the transfer from 1 minute has 60 seconds, and the specific volume is going to be 0.001 meter cubed per kilogram. So notice minutes and minutes cancel, meter cubed and meter cubed cancel, and we are left with kilograms per second, which is the unit of mass flow rate. So we have a mass flow rate of 0.33 kilograms per second. And we substitute into this equation. We have 0.33 kilograms per second. The value that we have for CP is 4.18 kilojoules per kilogram Kelvin. And the change of the temperatures that we have, we go from 50 Celsius to 10 Celsius. And the delta of Kelvin and the delta of Celsius cancel. Kilogram and kilogram cancels, and we're left with kilojoules per second, which is the unit required in the problem. And we find that this value is equal to 55.73 kilojoules per second, or simply kilowatts. In the next step, we need to determine the minimum power. For that, we need to first find the highest value of coefficient of performance, and that is going to be done by using the limit in temperatures that we have in our problem. So we have 1 minus TL divided by TH, and then we simply said that is 1 over 1 minus. Please remember that the temperatures must be in Kelvin. So the lower temperature, notice that it says that is from a source of 0 Celsius, so it's 0 plus 273. And the higher temperature, proceed rejects it at 30 Celsius. So we have it like this. We substitute the values and we find that the maximum coefficient of performance is equal to 10.1. And using this value and the value that we calculated in the previous step, the heat addition, the rate of heat transfer, then we find that the value of the power going in its minimum value is going to be the Q dot H that we found in the previous step, divided by the maximum coefficient of performance. And therefore we find that this is 55.73 kilowatts, and this is divided by 10.1, and we find that the minimum power is equal to 5.52 kilowatts.